Hey guys, welcome back. I hope that you guys had a good experience going through all the igneous rocks, learning about volcanoes. We're going to start stepping away from minerals and volcanoes, the origins of magma and all that stuff, and start looking at some new processes on the Earth. Namely, we're going to start breaking down those rocks, those igneous rocks that we've been talking about. And the process by which we break things down is called weathering. So here we can see we're going to begin a lecture on weathering. The next lecture will be on soils, actually. But here we see some weathering processes. There's water flowing over some rocks. Notice the rocks are being rounded and they're being smoothed and made smaller. This is a different kind of erosion over here. This is also done by water, a combination of water and a little bit of wind. And then, of course, here's another form of water erosion right here. This is the bottom of the Grand Canyon. This is the Colorado River. And you can see there's a little dam down here blocking it up. And we can even see the active process of weathering because when we look at the water, it's not that crystal blue color. It's got actual minerals and sediments stuck inside of it and floating down the river with it. So we're going to talk about those processes this lecture. So I hope you really enjoy it. This is one of my favorites, especially because it's through the weathering process that we get beautiful rock formations that look like this. Okay, so weathering occurs completely on the Earth's surface. This is a lot different than what we were talking about with magmas. Magmas occur down in the Earth's interior. Sometimes it occurs down even in the upper part of the mantle. This is a lot different, right? So this is a surficial process. This word surficial meaning on the surface. This is a word that only really occurs in geology. Nobody else uses it. So unfortunately, if you were to ever type this out, in any type of report, those of you that go on to future geology classes will have that underlined as being an unknown word. But anyways, it exists in geology and pretty much geology only. So Earth's surficial processes. Of course, weathering is the physical breakdown and chemical alteration of rock at or near Earth's surface. Here's a new one though, mass wasting. Mass wasting is the transfer of rock and soil downslope under the influence of gravity. Down here we have a picture of mass wasting. This is a highway, and I believe this is somewhere in Asia. The exact country escapes me, I don't recall anymore. But this is a landslide that moved down. This entire block of land moved down and spilled across the highway. Matter of fact, the only thing that stopped it from continuing across the highway was the fact there was a buttress or another abutment on the other side that actually stopped it from moving. So it just spilled out here into the middle of the highway, and you can imagine this is going to be literally a mountain of material that they're going to have to move to deal with. Okay? And then, of course, erosion is the physical removal of material by mobile agents such as water, wind, ice, and gravity. And that erosion is that process we were showing actually in the first slide, where the Grand Canyon, of course, the Colorado River at the bottom of the Grand Canyon had all those wonderful sediments floating around in it. So in order to do this, in order to start weathering things, it turns out we have to understand that there are two different ways that you can weather things. First off, there's mechanical weathering, okay, which is the breaking of rocks into smaller pieces. We're going to go into the second variety, which is actually called chemical weathering. That'll be the second half of the lecture. So we'll come to that here momentarily, or in a few moments. So there are four primary types of mechanical weathering. There's actually more than that if you want to take into consideration smaller ways of moving things. But anyways, the principal ways that it happens, that nature breaks rocks down in place and starts moving it, is this way. So frost wedging, which is the alternate freezing and thawing of water in fractures and cracks, which promotes the disintegration of rocks. Okay, this makes sense because when water goes into a crack in a rock and it freezes, it expands, right? It gets larger. And so every single time it fills in, it expands that rock. It sits there and breaks it apart. We're going to show pictures of where this has actually happened to rocks. As a matter of fact, we're going to show examples of all these types. Another one is sheeting, which is the exfoliation or the removing apart of the surface material. Of igneous and metamorphic rocks, you're going to find out that metamorphic rocks act very similar to igneous rocks as we go forward. At the Earth's surface as a result of a reduction in confining pressure. So when magma chambers form, they're formed at very great pressures down in the heart of the Earth, in the heart of the crust, in some places quite deep. And as a magma chamber, say a granite body, makes its way up to the top through erosion, the material is removed off the top. What happens is the pressure is reduced so that rock, that granite, actually has the propensity to want to expand somewhat. And that expansion actually breaks the surface of the rock apart. Okay, another way is salt crystal growth. So salt crystal growth usually occurs wherever, of course, you're going to have salt crystals forming, and that's usually along the coast. So sea spray or salty groundwater penetrates crevices and pore spaces in rocks. And as the water evaporates, salt crystals form and enlarges the crevices. So you get little bits of salt in there, and just as long as you got a constant supply of salt, that salt will constantly form crystals, and those crystals will constantly put a pressure to try and split the rocks apart. And of course, there's the old-fashioned way of doing it, right, is biological activity. That's disintegration resulting from plants and animals. Plants, here's an example of, this is a temple in Thailand. This is actually a pretty famous spot. And these ancient temples have these beautiful trees growing off of them. And these trees are basically trying to break the temple apart. It's biological activity. So that's plants doing it. Animals such as gophers are constantly ripping up the soil and the ground all the time. And of course, human beings do this too. We are actually one of those agents of biological activity that tend to rip apart rocks. So to understand kind of how these things happen over time, we can imagine that we're going to take a big block of granite. And this block of granite is going to be 4 surface units of area on the surface, 4 on this area. And essentially what's going to happen is you break it apart. So say we break this into 1 square unit pieces. What's going to happen is the surface area of this rock is going to increase. It's the same amount of rock, but the more surface area as you break it apart. Obviously, there's more surface area when you break it here and here than there is in the original rock. So what is the import of that, or what makes that so important? Well, it means that because the surface area is larger, it means that there's more regions or more area for chemical attacks to occur on the surface of that rock. So we're going to talk about chemical weathering as we go forward, but just have that in the back of your mind, that it makes it more susceptible. It also means that these bigger blocks also tend to break up much more easily in the process of erosion and weathering and become sands and silts and clays as we go forward. All right, so let's look at frost wedging. So we've got some of the basic ideas down. So let's look at frost wedging. Frost wedging, we described it earlier. In this case here, you have a crack up here in the upper left-hand corner here. This crack is filled with water, and as the water freezes, it expands. And of course, it exerts a force on the rock, and it begins to split it right along these edges here. And you can see that's what these arrows are implying. And every once in a while, you get enough splitting that goes on that this becomes unstable and falls off. And so here we see slightly tilted sedimentary beds, but that's not responsible for all of this. This talus slope, which is basically a big pile of rocks that fell off the side of the hill, basically form because of frost wedging that is occurring up here in these exposed rocks. And we even have patches of snow right here on the surface. So this is a pretty important process that's governing this. And we can see it's pretty active because there's no vegetation growing on all of this. The vegetation's all down here, but it gets to the talus slope, which is this, geologists like sometimes to refer to as trash, rock trash that comes off the side of the mountain. We can see it's all here. It's like a big apron of material. But again, no vegetation, so it's constantly covering it up. It's that active. Here's a rock that's been directly affected by frost wedging. Now there's no water in here, but we can see that there's a crack right here. And if we look carefully, you'll see a white, it's kind of a lighter color where that crack occurred. That's an old rock vein. And so of course the vein formed because there was a crack there, and then since then it's broken because the water's able to get into that same crack and split it up. Here's another crack going this way, another one coming this way, and they cross back and forth. And there's actually kind of a science to why it breaks the way that it does, but we may or may not get to that in one of the later lectures. We'll see. Again, you can tell from the landscape, this is a cold environment. As a matter of fact, this is a glacial environment. These are glacial features all around here. And this rock has just been busted to pieces by frost wedging. All right, another really cool way to break rocks apart, just taking advantage of the fact that they're being exfoliated. So here we have a deep pluton that's being formed. And remember, I was describing how it would be formed at a very deep pressure, so there's a confining pressure on it. And as it's exposed up to the surface, you get things, these fractures that will start to form at the surface. And these fractures are called joints. And here we can see those joints, these fractures forming all along here. You can really see them actually up here quite well. And so these joints is what they're actually called. Form along the edge of this, or along the surface here. And it's along here that these rocks break and the joints fail and the material sloughs off the side. Okay, we can see that there's no rocks. We can see that there's no rocks actually deposited here. It's all sloughed off the side. Okay, even better, here you can see that exfoliation or that sheeting even better than you could in that previous photo, right? Clearly we can see that the rock didn't form like this, it became like this. A lot of the times I like to think of it as a hard-boiled egg. You know, sometimes if you hard-boil an egg improperly and you go to peel the shell off, it peels off in these layers. It exfoliates just like this. So this reminds me of an eggshell pattern here. Okay, so it turns out that the process of exfoliation doesn't just occur down deep. It actually sometimes occurs right up at the surface. And so there's a YouTube video. It's at this website here. And this YouTube video, which I'm going to play right now, demonstrates exfoliation in action. And it's pretty exciting to see. So let's go ahead and watch that video.
Ho, ho, ho. Ho, ho, ho. Oh. All the way down. This whole seam now is active again. Lots of activity down below. It's still lifting. Did you see that? It just popped right up. Little piece flew into the air. Yeah, baby. Now maybe you'll be happy. Everything is flat again. All those pieces that were lifting just went back down.
Okay, so we're back. So you can see that this is actually it can be pretty exciting if you happen to be on it. Exfoliation being detected is it's something that's not always seen. It's actually rarely ever seen in nature, so that's the reason why that video was pretty cool to most geologists that might be studying this. But this is in fact an important way that rocks erode and weather in high mountain ranges. In the Himalayan mountain ranges, exfoliation can occur and take down entire mountainsides. There have been lots of reports of this actually happening, but it's never really been observed, let alone filmed. And so we know these rapid exfoliation events occur, and they make these massive sounds, almost like explosions. And so and you can imagine that in ancient times, that if anybody lived in those valleys, they would attribute this to some type of supreme being or god, goddess, or whatever it is. And Afghanistan had quite a few of those in ancient times. So anyways, neat stuff here, right? Exfoliation. Let's go to our next weathering agent. Okay, and that would be salt wedging. So here we see a picture of, this is a granite surface, and it's actually pretty heavily weathered by chemical attack. But here we have a salt crust that's forming. So this is actually right near the coast. And here we have a rock fracture, and in that fracture, there's salt. There's salt infilling the fracture, okay? And so this is a rock that is just being torn apart just by salt wedging alone. Okay, so this is granite being exposed to salt wedging on a coastline, and we get an idea of what's going on. Here's another fracture right here, another one, and they're all filled with salt. So this thing is eventually just gonna fall right apart. All right. Biological activity. Here we see a really cool, I believe this is a sandstone. The sandstone is being attacked by this tree, or this tree root, which is trying to get down to the soil down beneath. And well, not just the soil, it's where the water is also at. So trees do this, and of course animal burrows. We see this right here. So this would be called, by the way, root wedging. This is animal burrows. And we actually find both root wedging episodes in animal burrows in the fossil record. We find tons of these animal burrows that go all the way back to the time that animals arrived on land, which occurred during a period of time called the Paleozoic. Root wedging, we find root casts or evidence of old roots, and that goes back to about the same time. Really neat stuff. All right, so now we've talked about the physical weathering. Let's talk about chemical weathering. So there's two principal ways that chemical weathering works. One is it basically dissolves whatever the rock material is. And the dissolution or the dissolving of the stuff is usually aided by small amounts of acid in the water. Usually it's carbonic acid, sometimes it's sulfuric acid. It could be industrial waste even, industrial things like, sulfuric acid is one of the most common ones. Soluble ions are retained in the underground water supply. So those minerals that our drinking water is so famous for, they remain in the groundwater. And they could be there for many, many centuries. The other way is through oxidation. So that's the bringing of oxygen into the situation. There's an exchange of electrons that bring this about. And so an oxidizing reaction is any chemical reaction in which a compound or radical loses electrons, okay? So if it loses electrons. In this case, what is it going to be losing the electrons to? The oxygen, right? The oxygen tends to come and take electrons away from things. So it's important for decomposing ferromagnesian minerals such as olivine, such as orthopyroxene, things like this. And so here we see both episodes here. So this is actually this is a case of oxidation. So this is a lava flow, or actually a cave, a lava tube. And here's a person, a cave explorer coming down, and we'll notice that there's an old lava flow here. But because of the nature of this lava flow, it's been covered by water. It's down at the bottom here, and that water has oxidized all of those mafic, those ferromagnesian minerals, or the mafic minerals that are in here, into this nice red color. Okay. In this case over here, we see a cave. Down here at the bottom, there's actually water, so it's an underground stream of some sort. And above here, we see these sticks of minerals that are hanging down. This has been dripping down, and this is because the rock has been dissolving and in certain places dripping down, and through a complex process redepositing these things. And these are called stalactites. And down here, coming up from the bottom up, are called stalagmites, which are piles of material. And sometimes they fuse together, the stalagmite and the stalactite, into it, which we don't actually see any good examples of. Maybe this is the best one here, into a single unit. So let's consider, for example, how the weathering of granite occurs. We can talk about the weathering of basalt and whatever, but let's just go ahead and take the case of granite, because granite has things like quartz in it, and quartz, when it breaks down, it basically does a lot of physical, but it doesn't do a lot of chemical. So we find a lot of quartz in sedimentary rocks, which is where we're heading with this eventual conversation, or with this series of lectures. All right, so generally, it's chemically attacked by carbonic acid. So carbonic acid is generated in the atmosphere. We have water, which is in the rain, and CO2, that's what we breathe out. And that'll form carbonic acid, which is H2CO3. So the hydrogen ion attacks and replaces other positive ions. So it's this hydrogen right here. And more abundant products, or the most abundant product, I should say, is the clay minerals. So when you take anorthite and you add some water and some carbon dioxide to it, which of course is going to make your carbonic acid, you're going to wind up with a clay called kaolinite and a byproduct called calcium bicarbonate. And this is going to wind up in the oceans. If you take orthoclays, this is K-spar plus water plus carbon dioxide, you're going to get kaolinite, silicic acid. Now we have something new here. We're going to be putting silica into the water. And potassium bicarbonate, again, going to wind up in the ocean. Both of these will wind up in the ocean. And last but not least, albite, which is the last of the three of the last feldspars, plus water plus carbon dioxide is going to give you kaolinite. Remember, each one of these is going to give me kaolinite. Again, silicic acid, but my byproduct here is going to be sodium bicarbonate. So all of these things break down. This is a weathering granite that's been extensively chemically weathered, and the material is going to wind up resulting in clay, plus some silicic acid for the more felsic versions of the feldspar, as well as some type of bicarbonate compound that's going to wash into the ocean. And this will be consumed by organisms in the ocean. Here's some other minerals. We've already gone over the feldspars. So basically, when you take quartz and you break it down, you're just going to wind up with residual products of quartz grains and silica. Feldspars are going to give you the clay minerals and silica plus those ions. We just covered that. But amphibole and hornblende specifically is going to give you clay minerals. Limonite, which is a really interesting mineral. It's an ore mineral. It's a metal ore. And hematite, which is an iron ore. And into the water, it's going to release silica, calcium, and magnesium. So as a single mineral breaks up, it actually results in the formation, in this case, of 5 or 6 different chemical species that go into the environment. Neat stuff. Olivine, when it breaks down, it's a little bit more simplistic than amphibole. It just forms limonite, hematite, silica, and puts a magnesium ion into the water. Neat stuff. So there's several important alterations that are caused by chemical weathering to parent materials that get broken down. So here we can see a big block of granite again. Granite is our favorite because it's pretty resistant and it's pretty much all over the continents, and we see this all over the place. But the result is that we get decomposition of unstable minerals. And when we think of unstable minerals, we should think of the more mafic minerals as being the ones that are the least stable, and the more felsic ones being the most stable. For example, quartz is extremely stable, even at the Earth's surface. It also results in the generation or retention of materials that are stable, right? So it breaks down things that shouldn't be at the Earth's surface or aren't happy at the Earth's surface for thermodynamic reasons, and it creates things that are happy at the Earth's surface. So amphibole, for example, is not one of those happy minerals at the surface. It wants to become a clay plus all of those limonite and hematite and other things. So you get the idea. And that can result also in some really cool physical changes, such as the rounding of corners or edges. So here we see this block again. Let's go back to it. Notice at all, it doesn't really have any sharp edges to it. This is called spheroidal weathering. And the reason why this occurs is because these corners here have more surface area. Remember, we're talking about that surface area argument earlier in the lecture. There's more surface area exposed because we're being attacked in 3 different directions. But if you were coming in this side, right here, it's only being exposed to chemical weathering right at this location here. So this would be attacked in 3 directions. This is attacked in 1 direction. What does that do? That winds up wiping out the corners, and it slows down, by comparison, the rate of weathering on the sides. And so it turns it basically into a ball. Here we can see the background, several of these. This is a photograph that was taken in Joshua Tree. This was a photo that was taken in Joshua Tree National Park in California. Okay, so let's go ahead and formally describe what minerals are going to form at the Earth's surface at the expense of what other minerals that are now unstable. So we have to understand what is stable and what is unstable, because that's going to affect our rates of weathering. Okay, so advanced mechanical weathering aids chemical weathering by increasing the surface area. We just described that. So other factors affecting weathering are rock characteristics. So rocks containing calcite, such as marble and limestone, readily dissolve in weakly acidic solutions. And silicate minerals weather in the same order as their order of crystallization. Okay, so marble and limestone dissolve very easily, but this is different. Quartz, it turns out, is the most stable. If we look over here, quartz is most stable because it has the most silica and the most covalent bonds. All right, so here we got quartz, it's nice and happy. Here's muscovite. And as we look at this, we notice that this relationship is exactly the inverse of something we've seen before. It's the inverse of Bowen's reaction series. So it turns out that quartz is the most stable and olivine would be the least stable. And the pyroxenes and the amphiboles and the plagioclase feldspars, especially the calcium-rich variety, are extremely unstable. And they tend to want to break down and weather very rapidly in an acidic chemical environment. It doesn't take that much water to make that happen. So this, by the way, this is referred to as the Goldich stability series. It's basically the opposite or the inverse of Bowen's reaction series, which you will remember from igneous rocks. So the relationship between climate and weathering is pretty well worked out. So climate is basically going to tell us something about the temperature and the moisture, right? So temperature and moisture, climate is really an average, a long-term average of weather conditions over decades, even centuries. And so it turns out temperature and moisture are the most crucial factors. So chemical weathering is most effective in warm, moist climates. So if you got a lot of water and it's pretty warm, you get a lot of chemical weathering. You don't get a lot of physical weathering, but you get a lot of chemical weathering. Breaks things down. So when we look at our chart here, and that's what we're showing down here, is we can say here's the average temperature, so let's go to a high temperature, and here's our precipitation rates, centimeters per year. And if we come to, say, 200 centimeters per year at a high temperature, we're in the zone of strong chemical weathering. All right, now remember, this 0 is the point at which freezing occurs, right? So at this point here, we can say at 100 centimeters per year, at 0 degrees Celsius as being your average temperature, you get moderate chemical weathering, but you get a lot of ice wedging, right? Now, below that, you're not going to find a whole lot of chemical weathering. Why? Pretty straightforward. There's no water. The water's frozen solid. It's ice. So it can't do any chemical weathering. We get very, very little chemical weathering. So the style of weathering that predominates in colder environments are the physical weathering varieties. The breaking apart, the frost wedging of material is much more prevalent. All right. So at this point, we have kind of enough information to start looking at spectacular rock formations and starting to interpret them. Here we actually see a rock formation, and this is actually out of Utah. This is called Bryce, and these are interesting things. Now notice we got these almost kind of like pilings or columns of rock. And how do these things form? Well, the reason why they form is because we have something called differential weathering. Not all things weather the same way or at the same rate, right? You can have certain formations that have minerals that are more resistant than others. And sure enough, when we look at this, we'll notice that there is at the top here this darker rock, and that darker rock is refusing to weather. And so it literally protects all of the rock below it. Same thing here, that's that same rock here, it's capping it. Okay, and it basically is protecting this whole column of rock below it. Now these other ones, it's already lost their columns, and the ones that have lost it are starting to fall apart. Okay, but the ones that still have it stand nice and tall. And this is basically weathering right out of the side of the canyon here. Okay, really, really beautiful place if you ever get the chance to go to is Bryce Canyon. By the way, the word for these columns of rock are called hoodoos. It's an old Indian word that is still actually used by geologists, and these columns of rock are called hoodoos. Here's another hoodoo, right? This is a really neat hoodoo. So here's differential weathering. Here's a really soft rock that's underneath, but it's being protected up on top by something that's really hard. This is probably some kind of sandstone or tuff or something like that, which is pretty resistant. And here we can see it all throughout here, and it's protecting these spots through here. And as a consequence, it's able to create these columns beneath back here in the background as well. Cool. So anyways, I hope you enjoyed this lecture, and I really like weathering, and I think that it gives rise to some really spectacular features. The Grand Canyon was formed as a result of weathering and differential weathering, some of the formations we've seen here. But also, going forward, we'll realize that if it wasn't for the weathering environment, we wouldn't have the soils that we have. We wouldn't have the oceans being salty and producing the life that they produce. And so this is a very important process. It's a very important feature of the rock cycle. So if you have any questions, feel free to send me an email or put something on the discussion board for open discussion. Until next time, I hope you have a good one.